Okay, I'll wait a minute and then I'll start. In the meanwhile, please remember my request to, as far as you are willing to do it, is to turn on the video. I appreciate, Charles, that you are on. It's very nice of you. And, you know, the more people will be on, it will sort of free me from this surrealistic feeling that I'm talking to myself. So it's really nice to have more people on video. Okay, so I hope that you were able to watch what I recorded in lieu of the class last Monday. And I managed to do a bit more than the title of the slide file suggests. Actually did quite a bit more. I did the chapter on or a big part of the chapter on red-black trees. And the main thing that was left off at the end was that I didn't do the delete. And the issues there was that I found the delete a bit more demanding, and my understanding of what this class is all about, it is not supposed to be as both comprehensive and in-depth as courses that specialize just in algorithms. I'm supposed to give you nuggets and have certain coverage up to a certain depth of this material. And I think that I feel responsible to give you some examples of delete, but if this example was too complex, I don't feel as obliged to do that. So I'm going to switch over to another very important data structure, and I'm going to demonstrate the full queries of a dictionary. So just to remind you, a dictionary is a data structure that supports search, insert, and delete. So here I'm going to demonstrate the delete in full. Now, I'm going to explain why I'm going to rely on the text taken from a chapter in my parallel algorithms course for 2-3-trees, which is the data structure I'm going to describe next. So you may wonder why. I owe you an explanation on that. You will see that the parallel version uses slightly more, in terms of a constant factor, more space, but unlike all other deterministic data structures that do delete in logarithmic time, it does it so much simpler, and I will make a point of it when we get there. Okay, so for the material in this chapter, it is a version of chapter 18, or the materials there, but what you are responsible for is the material in my class notes, and you should feel free to omit the parallel versions, because that material advances from serial to parallel version. So you are responsible for this class only for the serial versions of this material. Okay, so let's proceed. What is a 2-3-3? So as we have seen, whenever we talk about these combinatorial data structures, they are divided into really two components. One component, which I like to call the combinatorial side, where so there's no content. I'm just describing to you what are the nodes and the edges that you see. So what is the combinatorial side here? First, it's a tree. It's a rooted tree, like here. So here, I mean, in this figure, just imagine that you have a line here on top that closes it. So this is a node in a tree. These are the immediate children of this node. These are their children, and these are the leaves in the node. So let's see how we define a 2-3 tree. A 2-3 tree is a rooted tree which meets exactly two requirements. One is that if a node is not a leaf, like this node and all of these nodes right here, it has either 2 or 3 children. Okay, so this is a requirement which is, again, it's on the syntax. Remember, I'm separating syntax from semantics. Now I'm describing only the syntax, how this looks. No content whatsoever. So there is no data yet. It's just the structure. So ignore all the numbers written inside here. They have a meaning only when we put the syntax into the semantics into the syntax. And the other thing which defines a 2-3 tree, so I already said, we have the first description, the first requirement that every node will have 2 or 3 children. The second is that no matter where you are in every node, if you look at its subtree, the number of the distance from the node to the leaves in its subtree is the same to all leaves. So if you tell from here to some leaf, it's 2. So from here to every leaf in its subtree, it will be 2. Okay. So these are the two requirements. I repeat the two combinatorial requirements. Every node has 2 or 3 children, and the distance between a node and all the leaves in its subtree is the same. Okay. So after I define that, let me just, for the mental exercise side of things, consider a different definition of 2-3 trees. So here is a different definition. The first requirement is the same, that every node will have 2 or 3 children. The second requirement, I'm replacing it by limiting the requirement that all the paths from the root, only the root, not all the other nodes, to any leaf of the tree is the same. So is the different requirement clear? Here, I originally asked the length of the path from every node to the leaves in its subtree will be the same. Now I'm replacing it by something that looks like a less strict requirement, that this requirement will apply only to the root. And the question I wanted to raise to you, are these two requirements equivalent? It should be clear that the former requirement clearly implies the latter, right? Because if from every node, the distance of the path to its leaf must be the same, the root is one of these nodes. So trivially, the former requirements implies the latter. But what will be more remarkable is if the latter requirement implies the former, right? And the question is, does it? Anybody wants to give a guess? Could I have replaced the second requirement by the second requirement, the requirement that all the path lengths are the same, by asking for it only from the root? Will I get, will it be a different definition?
I think they are equivalent.
What did you say? Speak up.
I think they are equivalent.
You think they are equivalent. Can you reason why?
Not clearly, no. But I can't see how, if all the paths from the root to the leaves
Somehow
are
I
equal.
don't hear you, and I think all the others.
Okay, let me check on my system for a second. Um, is this more clear?
It's a tiny bit better.
Okay. So I don't see how, if we ensure that all the paths from the root to the leaves are equal,
You
that
don't see
no,
what?
I don't see that they how they could contradict with each other. So if we ensure that the paths from the root to the leaves are equal, we subliminally ensure that from every node to the subtree, for every
Right.
subtree, they are equivalent as well.
Okay. So maybe a different way. I think you got it. Basically, you say let's pick a node which is not the root, and suppose that it has a path to different leaves which are of different lengths. It is trivial to see that this would have implied that we will also have two paths of different lengths starting from the root.
Exactly. Yeah.
Very good. Okay. So this is the proof. Very good. Thank you very much. Okay. So now I wanted to continue and define the semantic side, because so far it was only structure. So now give me a set, and I wanted to map the set into a 2, 3, 3. So the idea is basically the following. So unlike red-black trees, you see in one immediate waste where we store original keys only in the leaves, not in internal nodes. Okay. So basically in a 2, 3, 3, the set is stored in order, already sorted in the leaves. Okay. But what is the definition of a 2, 3, 3 is the following. Every node has either 2 or 3 children. So you store in every node as many keys as the children that it has. So for example, the root has 3 children. So you stored 3 numbers. What is this 17? 17 is the largest value on the left subtree. Since it has 3 children, it has a right and a middle subtree. So this is left, middle, right. The 28 is the maximum value in this subtree. 39 is the maximum value here. Okay? And the same for all the nodes that you see here. In this case, we see a node with 2 children, only left and right. And indeed, what we keep is exactly the same. Here, the 21 is the largest value in this subtree, and 28 is the largest value in the right subtree. So this is in the left, and this is in the right, and there is no middle. For that reason, there is no number here. Okay, so this is the full story of how you put semantics into a 2, 3 tree. Questions about that? Okay, so the next thing I want to demonstrate is how you can do search in logarithmic time. So give me a key. Let's say the key is 30. Okay. So I need to, and you ask me, do I have 30 in the tree? So what will you do? You see here that because you have 28, it basically cannot be here, right? 28 is the largest value in this node. So if it is here, it got to be only to the right. So you go to the right, and it is less than 39, and we are going to discuss the 39 soon. So in any case, you go to the right, and now you compare it with 33. You conclude that if it is there, it's on the left. You go to the left, and you find that you don't have a 30. Okay, you can proceed all the way. And if you look for 31, you will find the 31 using the same route. Now, let us ask ourselves, is there anything that you can observe when I do this search which is redundant? Like, look at the question I asked you. When I look for the key 30 or 31, was there a value that I never looked at? I claimed that I didn't really need the 39 because if I were to not to have the 39 here, only the 28, this would be enough to conclude that I need to go to the right. Is that clear? Now, if you give me a value such as 40, which will allow me to reject the, to tell you, to reject the query, say, no, it's not there, at the root, this would not have saved me much because if I'm willing to pay for search logarithmic time, I could actually go and go all the way to the leaf and find that 40 is not there. So I don't really need the 39 to match the logarithmic time. Now, one quick observation, which I sort of skipped. So is this clear? What I just said, that basically you don't need the maximum of the right tree, meaning whenever you see here 3 numbers, 2 would be enough for search. Whenever you see 2 numbers, 1 would be enough for search. Is that clear? So the question is, so why am I bothering you? Why am I doing something which looks such a waste? So the answer to that is really twofold. The native answer is because this makes the algorithm parallelizable. And I'm going to wave my hand a bit and tell you why. But what is of biggest value to this class is that it will make the delete so much easier. And the way it will make it easier, first it will allow me to present to you the delete in fullness. And the second argument is that it allows parallelization of things. So now, one thing that I actually wanted to run by you quite quickly, because it's not a very difficult argument, is can you argue why, if you have n leaves, the height of the tree is big O of log? Can you say why? Can you try and reason why the height of the tree must be big O of log n if you have n leaves? Clearly, if it was a binary tree, it would be trivially, and it would be balanced, it would be log base 2 of n, right? Would be a full tree. If I had a ternary tree, meaning every node would be, it would have 3 nodes, it will be log base 3 of n, right? And that's exactly the point, that because log base 3 of n is a constant factor away from log 2 of n, right? Because you take log 3 over log 2 and log 3 base 2, and this gives you the factor of moving from one to the other, which is a constant factor. And this is the range. If I give you n nodes of the possible heights, you can conclude that it must be order of log n. Is that clear? Because the lowest the height can be is log base 3 of n. The highest it can be is log base 2 of n. Okay. So, so far for the search, any questions about the definition of 2, 3 trees and the search? Okay, so now going to move to the first query, and we discussed this query of insert. So I'm going to show you how to do the insert here. And one thing which I really want you to appreciate here in the description of the algorithm is how important mathematical induction is for everything that we study. Because what I'm going to give to you here is really, I'm going to fit into mathematical induction in a way that will make it clear that by defining one step, I define for you the full algorithm. Okay, so I'm going to demonstrate it on this example, where what I ask you to do is to insert the value 12 into this 2, 3, 3. And I'm going to demonstrate the insert algorithm using this example. So what will be the idea? The idea is that you start with a search. In the search, you find that 12 is not already in the tree, because then you stop. And then you figure out that if 12 were to be there, it should be between 11 and 14. So the algorithm actually requires that you will find the immediately larger key in the tree, 14 in this case. And in a way, you are anchoring, you are absorbing the value 12 by making it sort of a parasite on 14. However, this immediately invites a question. What if the value you want to insert is larger than the largest? I'm going to wave my hands and explain and argue that you can do something symmetric by attaching it to the immediately to the smaller element which is closest to it. So if it is 40, you will attach it to 39 and you do something symmetric. I'm going to skip it, sweep it under the rug, but because it is more a detailed part, some detailed type that you can fit in. So here's the idea. Look at the 12. Where would I like to fit it? Here. So suppose I fit it here, and I'm already aware of the 14. What did I get? If you look at the situation and you sort of close your eyes to, or imagine a window, where in your window, you go up to the parent level. That's your horizon. You don't look beyond the parent level. So you look up to the ABC level here. And you look at the leaf level. So imagine that you operate within this window. So what happened in this window? We entered an orphan, a node which has no parent. Okay, what about everything else? Everything else is legitimate. Meaning, with the exception of having an orphan, which definitely 2, 3 trees do not recognize this concept, because it should be a tree. Okay, it should be 2, 3 tree. Outside this infringement, everything else is fully legitimate. right? And here comes the basic description idea of the algorithm. The basic description idea will be to take this infringement and push it one level up in the tree, where everything at the leaf level relative to the immediate parent level of the trees is legit, but the infringement will shift to the window between the parents and the grandparents. Okay, and if the infringement will be exactly the same or it will disappear, then I basically finished. Why did I finish? Because if I give you a procedure which allows me to advance from level to level, the number of levels is finite. And to the extent that I may have slightly different treatment if I reach the root, I can give it to you, but by the ability of taking the infringement and move it in one direction and get rid of it, I'm doing something which is really similar to, if you think to an iteration of bubble sort. When you have a bubble of infringement and you push it all the way, you get rid of it, problem solved. So to the extent that I can push the infringement one level up, I'm done. Because what will I do next? I will do the same thing, push it one level up. Then I'll do the same thing until it is absorbed or disappeared or whatever, but I never need to come back. So that's the basic framework. I hope that this framework is clear. So what I need to show you now is how do I push the infringement one level up. So remember this picture, an orphan where everything else is legitimate and my horizon is the leaves and their parents. So what's going on next? I actually take this node C, which if I were to include another child under C, it will have 4 children, which is unacceptable, right? According to the definition of 233. So I split the C into 2 nodes, C and C left. And by doing that, what did I create? I created a situation where everything from this level and down is legit, right? So if you put now your window where it used to be, you have no reservations. All the nodes here have either 2 or 3 children, right? Where do you have a reservation? Well, if you look at this window between the ABC level and the age IJ level, okay, there you have an orphan. Everything else is legitimate. So do you see why, by doing this very small thing, I actually created a situation where did I draw it now? I'm surprised. What's going on? Yeah, so by adding this link here, trying to edit, what did I cause? I wonder what happened here. I don't know where this appeared from. I'm surprised here. Anyway, so it's funny. I don't know how it came to be here, this link. Anyway, so this is the new situation. So what do I need to show you, basically? That I can push it further. And I claim that what I did before is as valid, meaning when I have this situation, I need to take age, which will now, if I try to incorporate this orphan into it, I will need to split it into age and age left. And what will happen is that Now I'll have age and age left. And from the K point of view, now if I look at the age IJ level, my window, I move it up and I include K, what do I have? I have an orphan and everything else is legitimate. So what will I do next? I will break the K into K and K left. And now I got a new situation. And what is the new situation? That I don't have a root anymore. But now it's trivial to finish, right? Because I add a new root, the tree becomes higher by 1, and the problem is gone. Now I don't have anything, any infringement. Okay? So this is what I just described to you is the structural changes introduced in the tree, which I believe are very intuitive and are not very difficult to follow. Now, the claim is that the complexity is logarithmic, and why is that so? Because when it comes to the structure, it should be clear that I'm investing constant time level. I'm doing some constant number of things. The one thing that I still need, I believe, to convince you is that when it comes to updating the values, which I sort of swept under the rug, because obviously, as I go up, I need also to revise the values that sit in these internal nodes, right? In the same way that here I had 11, 14, and 17. Obviously, when I have C and C left, I have 11, 12, and 14, 17, right? And then I'll go up, I will have here 3, 8, and then I'll have here the whatever proceeds, I'll have 12 and 17, and then I split. So I need to be sure that I can copy the values. But the reason that this is actually simple to do is because I always keep the maximum and I keep whole trees. So I never need to come down, collect new values and go up. So it's the unidirectional flow of insert, which, let me tell you, is not unique. That's not where we need the third value that I mentioned before, which looked redundant. You could do it even if you had only 2 values. But what I'm going to demonstrate to you is how the third value is going to allow me the same simplicity even when I do delete. And I will try to explain it. So do you all agree with me that I established that complexity of insert is logarithmic? Okay, now I'm going to discuss delete. Now let's think about it. When it came to insert, what did I choose for my example? I chose for my example a situation where I inserted elements was for nodes which have 3 children. Why did I choose that? Because insert becomes challenging if the node under which you insert a new node is full to capacity, right? I mean, if I had to insert a 7 here, think what would have happened. I would insert a 7 here, put 7 here, and I go home, right? So the case where you have only 2 children is really easy. And you know, if I were to include a 4, the 5 will shift here and the 4 will come here. Easy. Insert becomes a challenge when you have 3 children. In an analogous way, when does delete becomes challenging? When you have 2 children, right? Because if I had 3 children, I have to remove 1, no problem, I remove it and I'm done. But if I need to delete when I have only 2 children, it means that I remain with 1. And remaining with 1 is not legit. Hope this point is clear. So for that reason, not surprisingly, I consider in the example I'm going to present a balanced binary tree. where all the nodes have exactly 2 children, and the deletion of any of them will require structural changes. Okay, so let us try and reason basically using the same structure about delete. So suppose that this is my tree, and I'm to delete this node whose key is 4. Clearly, by doing that, I create this infringement where the level between the leaf and the parent has a node B, which now has just 1 child, illegit, not legitimate. So how am I going to overcome that? Exactly the same idea as before. I'm going to take the infringement and I'm going to shift it 1 level up. So if here the infringement was at this level of A, B, C, D towards the leaves, now I'm going to shift the infringement so it will be between the A, B, C, D and B and F, and E and F, I'm sorry. So I shift it 1 level up. And what will happen later, I shift it 1 level up until I get rid of it. So it's basically the same inductive mindset. Okay. So now let's take this example where I remove these 4, and now B has just 1 child. So what can I do when I shift it 1 level up? I will try to negotiate with my sibling A, and had A had 3 children, I would have shifted 1 to B and stopped it there. But since A also has only 2 children, my only recourse really, if I want to resolve it locally, is to move the 3 to A, make it make the 2, the middle child of A, 3 the right child, and now I am going to discard B. So when I shift it to this level, look at what I have. Everything from at the lower level, at the A, now B is gone, A, C, D level, to the leaves is legit, because if you look at what's going on at this level down, all the nodes have either 3 or 2 children. But the E now, and the window that goes between E and F and the level below it, has an infringement, which is that node E has only 1 child, A, because B is being discarded. So what will I do next? I will do exactly the same. I will look to my sibling, and if my sibling, again, has only 2 children, I have no way but to discard one of the nodes. And which node will I discard? You know, it's a matter of the arbitrary way in which to design your algorithm. I could have discarded E or F. It doesn't matter. I need to discard one of them. So here I give priority to the left guy to remain alive. So I kill the F. Okay, and make all the 3 children that remain in the level just above the leaves to be children of E. So F is now being discarded. So I finally discard F, and look at what happened. It becomes the new root. So just to be clear what's going on, by discarding F, what did I do? I create a situation where G has just 1 child, but G is the root. So I have no way of shifting things around anymore. A root that has 1 child has no right to exist in a 2-3 tree. So I just knock the root, and this is the final tree. Okay, so now you may wonder, as I describe this, what will happen to the values that I need to shift around? And what you see as this algorithm advances, I described to you some situations that didn't necessarily happen here. But no, actually, they did happen here. Just a second. So look at what happened here when I advanced from this level, from this, in the very first stage, I advanced from here to here. Remember that when I looked at these values here, I had 1 and 2, and here I had 3 and 4. So when I made these 3 a child of A, observe that I didn't need to go down and get the 2 value. The 2 value was here. I only needed to shift it to the left. But remember the alternative I mentioned before. If you have only 2 children, you need the maximum of only the left one. The right one you don't need. So if I were to operate under that, what would I need to do when I make 3 the right child of A? I would have needed to come down, figure out that I have a 2, put it here. So I couldn't locally, within node A, get the 2. Now here it looks really benign because you are just a level above the leaves. So what's the big deal of going down? But if you have this situation for a node which is, say, logarithmic number of levels above, you would need to come down, get the value, and bring it up. So do you see why this will be much more complex? Now, why is this so significant? So the point I was trying to make, that the data for all changes is always available locally, because when you shift and you have this maximum value for the right subtree, all the data is available here, and you may want to visit this with a numeric example all the way. This takes a logarithmic time, because the process I described here is really inductive, where you spend constant time per level. Now, just to give you some intuition about the parallel algorithm here, and again, the next time it appears now that I'll teach a parallel algorithms course will be only in the spring of 2022. But the basic idea there is to benefit from the unidirectional flow. And there is some significant subtlety in the parallel algorithm, because the way you do it is, first you take some special case where you don't insert or delete elements which are too close to one another. And you show that you can use pipelining to do that, go in one direction and finish. And then you need to do something which is much more sophisticated to treat the general case, where you can delete any number of elements at once. And you need to resort to concept of pipelining in software to do that. Again, this is beyond scope for this class. I just wanted to mention it because your main benefit from this algorithm is that it's much simpler. I hope that you agree that this was a relatively simple delete algorithm. But the original native motivation for doing this was a parallel. Okay, one thing that I wanted to say, just for your background, is you may wonder, why are we actually even bothering with 2, 3 trees? After all, if you remember this picture, unlike red-black trees, there is a significant waste of space here because keys are only in the leaves. Right? So clearly you don't use the internal nodes to keep keys. So why is it beneficial? So it turns out that historically, and of course it's debatable how future systems will look, bit trees have been playing a major role in databases, which try to sort a big number, to store a huge number of elements. And I'll give you just one example, because the concept of 2-3 trees actually is a special case of what's called bit trees. In bit trees, you allow not only 2 or 3 children, you allow between 2 and whatever number. And in data structure, sometimes they use a number as high as 1,000. So any number between 2 and 1,000 can be there, because the flexibility allows you to actually create always a balanced tree. So this is why it is attractive. But why 1,000? So the reason is the following. Think about a tree which is really a 3-level tree. The root has 1,000 children. The leaf below has 1,000 children. The leaf below has 1,000 children. And I'm sorry. The node, the root has 1,000. The node below that 1,000 each. And here every node has 1,000, and this is the leaf level. So this in itself already allows us to include 1 billion keys, which is quite a significant number. Okay? So why can this be beneficial to have a structure like this? The answer is that it has to do with hardware, with the type of hardware that appears in the commercial world, that I'm going to elaborate a bit on, but within limit. I'm just going to give you some comments on, and you can definitely argue that some constraints I'm mentioning are a thing of the past, but I don't think that they are just things of the past. How long they will remain relevant, who knows? So basically, the idea here, and since you are all in ECE, you are all very aware of the concept of a page in computer architecture. We can bring a whole page from memory for a price which is not much higher than bringing one item. I guess many of you have heard this term, page in connection to memory. And how big is a page? Again, it depends on the hardware, but makes sense to think about it as being like 1,000 keys or something like that. There are some technologies where this is the right number. So the point here is that a classic support for data storage is a disk, where the disk looks like that. You have here a spindle, you have multiple tracks, like here, and they all physically turn around, and you have an arm and a needle or a reading head at the end of each arm. And now, as you move it, you move all the arms at the same, so you read the same track across from all the disks and from all the platters. So it is all considered a disk. And then you can retrieve everything that doesn't require movement of the arm much faster than if you require a physical movement of the arm, which actually starts giving you this concept that to the extent that you will be looking for something in the same page, it will be less, because you can upload the page to main memory, treat it there. So the way that you will usually process something like this is that bring a page. So suppose I'm to do a search. So how will the search look? I will go here. It will ask me for some key. Based on the keys, 1,000 keys here, I'll figure out that the value you are looking for is somewhere here. So I will go here, get a page. I look at the page, I process it, it's in my main memory. And based on that, I decide that I need to go to one of its children, which is somewhere here. Go here and I figure out whether the value is here. So in terms of physical accesses, which cost me a lot of time, a huge overhead, I did that 3 times, right? Now think about the alternative. The alternative is that I were to solve, to store this tree in something which is a binary tree. A binary tree would mean that instead of having 3 levels, I will have the logarithm of 1 billion base 2, which is
9.
It is 30. Is that clear to everybody? So this is the advantage. So now you can argue now that as we move to high bandwidth memories, all the new technologies and stuff like that, this equation starts shifting and it becomes a question, what is right? You know, you have the data, you know, you have a network sometimes, whatever. The point is that you can definitely imagine a situation where this was or will be valuable. And overall, I think what remains, and maybe the factor is not as big as it used to be in the old disk days, but the idea, you still have a notion of spatial locality, what's called in computer architecture. And whenever spatial locality works for you, you may want to use the parameters that the architecture suggests in order to find the right balance of whether you want to have a 2-3 tree, a 2-3-10 tree, or a 2-3-1000 tree. Okay, so how many nodes will be justified? Okay, this is the end of the 2-3 tree section. I hope that it's clear that what I promised to deliver, which was not only a search and insert, but also delete, has been done. And let me know if you have any questions about this chapter. Okay, if not, I will move over to the next chapter. So I'm going to do a stop share and going to share again. Okay, so I'm going to move on, and the next chapter will be chapter 14. So chapter 14, while we are going to focus only on red-black trees, represents the following opportunity for understanding that in spite of the fact that my data structure presentation focused on dictionary data structures, where you support search, insert, and delete queries, we could use this data structure for other queries. And meaning they are much more robust in the sense that whenever we need data structures, we need to ask ourselves whether we can somehow support them by an add-on to a data structure we are familiar with. Now, I'm going to present this concept of augmenting data structures for other queries exclusively for red-black trees, but you will not need much imagination to see that you could apply it to 2-3 trees or to max heap even, or to binary search trees and so on, more general than red-black. Okay, so the basic idea is what other queries I could add. And again, this does not mean to be exhaustive, just to demonstrate to you that these data structures are more powerful than just dictionary. So I wanted now to show you another family of queries that I could process if I were to properly update the data I store in say, a red-black tree or binary search tree. So what is an order statistic query? OS of xi. So x is a node, and I means find for me the I smallest element in the subtree rooted at x. Okay, so before, what was a search query? A search query, I would give you a key, and you need to resolve whether the key is there or not. Now I'm asking you a very different question. I'm asking you, what is the typical median question? What is the median? Or what is the I smallest question? We discussed that before. And in order to be able to resolve this, we are going to extend this query in a way that for every internal node of the data structure, like red-black tree, I'll be able to answer the question, what is the I smallest in the subtree rooted at that internal node? So, and the question that I'm going to ask here is how to augment a data structure so that the following can be done efficiently. Both address the query itself, meaning show you how to do it as where it replaces a search. And the other thing is, remember what was attractive about these data structures, that they were amenable to changes such as insert or delete. So can I still update the values that I need to keep in an efficient way when I don't only answer the query, but I also keep changing them? So can I maintain the augmented data structure? Okay, this will make it fully compatible with the dictionary situation we had before. So is the challenge clear? So I want to be able to respond to this query and also to be able to continue to be able to respond to it if my data structure goes through an insert and delete. So the idea is actually not very difficult. And I'm going to demonstrate to you how to do that in a binary search tree, and in particular in red-black trees. So what you have here is really a red-black tree, but for what we are discussing now, just think about it as a binary search tree. Okay. So let's see what's going on here. So remember that for binary search trees, what we have is really what you see here is the higher value. So the novelty is that now instead of just keeping one value at every node, we keep two. an upper and a lower value. The upper value is exactly what we saw before. So this 26, 17, 41, and all of that are exactly what we saw before. These are the keys. And just to remind you what's going on in a binary search tree, you want to find whether 18 is in the tree. So you compare it to 26, 18 is smaller, you go left. Compare it to 17, larger, go right. Compare to 21, smaller, go left. Compare to 19, smaller, go left, it's not here. Right, so that's how the upper values are, no change there. What is the change? What is the new thing? Is that we keep as the lower number a size of the rooted subtree. Okay, so now when I have 20 here, what it means is that there is a total of 20 nodes in this rooted subtree. And why do I have a 1 here? Because it's a leaf. There's only one node in this. Here you have 12 because you have 12 here. Here you have 7 because you have 7 here. And it's no surprise that it's 20 because 12 plus 7 plus 1 is 20. Okay? So clearly, if you look at the two children of a node, they should sum up plus 1 to what you see at the node. Okay. So these are all the fields that we need. And now, let's ask ourselves, how can we resolve this question? So let's ask ourselves the following question. I'm giving you all this set represented by red-black trees or binary search trees. It doesn't matter for that question to be asked. What is the 9th largest element here? Or 9th smallest element? I'm sorry, 9th smallest element. So how will I resolve that? I come here, and what do I need to look at? Where should I go to find the 9th smallest element? I know that this guy has 20 descendants. How will I decide whether to go left or right?
You should go left because 9 is lower than 20.
No.
So no?
No, because if I were to look for element number 15, 15 will also be lower than 20, but I would not go left. You see why? Because you have 12 here. So element, the 15th smallest element, I had to go to the right for that. You see what I'm saying? You understand what I said?
Oh, yeah, yeah.
So the reason is not because 9 is less than 20. The reason is because 9 is less than
12.
exactly.
So here we go left
Because 9
because
is less than 12.
yeah.
Is that clear to everybody? So the fact that 9, Ahmed, if you can put yourself on mute, I think we may have some traffic noise coming from you. Okay, so the issue really is to ask whether it's less than 12. So what are the possibilities? Either it is less than or equal to 12, and then you go left. If it is equal to 12 plus 1, what is the answer? What is the 13th smallest element?
The root.
26, exactly.
Yeah.
And if it is larger than like 15, what will you do?
Yeah, we will go right there.
No, but what will you look here? Will you still look for the 15th element?
For the 8th element?
No, you look for the second smallest. Because by going right, you excluded 12 plus 13, right? So you already said, I know that by going right, I already took into account 13 elements which are smaller. So here I will be looking for the element which is 2, right? So let's continue with that. So suppose with the 15 example, I would go here, look for the 2. Here I compare 2 to 5. When you are at the node, you look always to the left child. 2 is less than 5, right? So I go to here, and what will I do here? Here I will look to the left. I see that. So what is the second smallest element? Speak.
Yeah, 30.
30, right? Because it's exactly like the 13 here, because it's 1 plus 1, which means 2. Okay, so that's the basic idea. The basic idea is always look at the size of left parent. And this is the formula. Either you go there, or if you go right, here it's as if you go up. Here it's going down. You're going down. You subtract size of left parent plus 1. Go right. Okay, so is this clear to everybody? So clearly, by adding this size quantity, what have I accomplished? I accomplished the ability to search for what I declared here under this query, meaning find the node containing the I smallest element in the subtree at that node. And that's what I keep. And so far, just to clarify, I have not considered at all the difference between general binary search trees and black trees, right? I mean, the fact that it's red or black doesn't matter here at all, right? Because red-black trees are a special case. So far, for what up to now, the difference between the special case of red-black trees as opposed to binary search tree didn't show up at all. And now the question is, will I be able to maintain it? So, as you may remember from what I presented in the lecture of 2 days ago, which was recorded, primitive supporting maintenance in red-black trees was rotate, either left rotate or right rotate. So the only thing I need to convince you here is that to the extent I had the correct value of size prior to a rotate, I can figure out the correct value after using some local operations. And to the extent that to the extent I have it here, if I do a right rotate, I'll be able to adjust these values here. And if I have this situation, to the extent I do a left rotate, I'll be able to compute the right values using a rotate. That's the only thing I need to convince you. Because what we saw is that in order to maintain red-black primitive, and didn't present to you the delete case, the textbook makes it clear that this is the main issue or the main primitive that guides both inserts and delete. So can I maintain it? The answer is I can, quite trivially, because think about it. And it's enough to go from here to here just to show the point. So suppose that this is the correct size values where is the parent of X. Y has a total of 19 nodes. X has 11, which means that the right child of Y has 7. It somehow is into 6 and 4. Okay. So now, how will I be able, if I were to do a right rotate, where X will be the root, will move to the parent state, and Y will become a right child. So here, Y is the parent, X is the left child. Following a right rotate, X becomes the parent, Y becomes the right child, right? So let's see how I compute this 19 and 12, given that I know, right? How will I compute? So the first observation is trivial. This 19 got to be this 19. Is that clear to everybody? Because this is the parent of the same ordered subtree that here Y was the root of this subtree, and now X is the root of this subtree. What happened to the number of nodes? Same. So this is a very simple update where this 19 becomes this 19. No, not much thinking, not much thinking there. Now, the key value, in order to figure out this 12, the only thing you really need to do is to look to the right child of 4, because it will migrate from the left, from being a right child of X to being the left child of Y. So if you give me this 4, what will happen? This 4 will be subtracted from 11, right? And you need to figure out how to add it to the other side. So now it will be added to the 7 here, and to get the 12. Why? Because 7 plus 4 plus 1 is 12. So this 4 holds the key, because that's the only shift that happened. Okay, so it's pretty similar. You take this 4, you add it to this 7, you add 1, and that's the 12. All of this is very local. And it is a trivial exercise to convince yourself that the same happens when you move from here. Okay, so the next thing that to do is to consider a pretty cool problem that is derived from computational geometry. And I'm definitely not going to complete this today, but let me just start with the problem and what I would like to represent here. So imagine that we have a straight line where my basic elements are intervals. So what does an interval on a straight line mean? It means that it has a left low point and a high point. So if my interval is I can fully characterize it by the low point and the high point. So instead of having just a single number like with the keys, here, any element I have has really 2 keys, if you low and high. And they fully characterize the interval, because the low tells me where it starts, the high tells me when it ends. And what I would like my data structure to represent is whether they, or be able to address, is whether they overlap. And more particularly, I'd like to have a data structure where if you now give me another interval, a new interval, I would like to know if that interval intersects anybody of my intervals or not. And if it does intersect, give me one that it does intersect. Okay. So this is the type of augmentation, augmenting data structure. Remember the chapter in which we are, that we would like to reason about. So the new setting is a computational geometry setting. I would like to build a data structure where you give me a bunch of intervals, and if I give you another one, you will be able to tell me very quickly whether it intersects one of my existing intervals or not. So with this motivating problem, I'm going to finish today's class, and the next time we meet will be already in the month of October. It will be Monday. So that's the end of it. If you have any questions about what I presented before, please raise your hand. Otherwise, our class is over. Okay, bye.